Hey class, so today we're going to be doing an introduction to radical expressions. The radicals you guys have seen before are most likely just our square roots, but we do have other types of radicals that we're going to work with this year. Mainly, this number out here is going to change a bunch. It can go up to higher numbers. Usually with our square root, we just assume there's a 2 there. We don't normally write it, but we're going to see what types of radicals happen. And we have other numbers there. But first, it'll be a little bit helpful for us later. So I want to review some of our laws of exponents. Let's start with our products of powers. Product means multiplying in powers. So say we have x squared. We're going to multiply these together. X squared times x squared, that's the same thing as x times x from our x squared times x times x from our other x squared. So we get x to the 4th power because we have 4x for multiplying by. And in general, we want a rule for it. Make a little space here. If we have a product of powers, say we have x to some n value times x to some m value, just two different numbers. What we can do is we can add them together. So for us, 2 plus 2 is 4. All right. Our quotient of powers is similar. Can move this down to make a little bit more space for us again. Our quotient means is to divide. So for our quotient, we're looking at, say we have x squared divided by x. Do the first power. This is the same thing as x times x divided by x. One of my x's would cancel, so we'd be left with x. The way that we can write this for a general notation, say we had x to some power n divided by x to another power m. All we had to do is subtract the powers. This would be equal to x of n minus m. Oop. Okay, let me try erasing that. Computer's having a little bit of a hard time. N minus m. So for us, 2 minus 1 is equal to 1. Okay. The reason that we're subtracting m is effectively all of the x's on the bottom are canceling out from the top. Okay. When we have negative exponents, a little bit more space again. What our negative exponents, give me my pen back. Yep. Okay, so our negative exponents, say we have x to the negative 1 power. What this is actually representing is normally our power is representing repeated multiplication. So if I have x to the squared, that's x times itself twice. What this negative does is instead of multiplication, the opposite of multiplication, which our negative sign means opposite, would be to divide. So with our negative exponents, we can flip it to the bottom. Similarly, if I have a negative exponent on the bottom, it flips up to the top. All right. So another example of this could be, say we had x to the negative 2 divided by x to the negative 3. This would be the same thing as Negative on the bottom comes to the top, and negative on the top goes to the bottom. So you have a negative exponent, flips from the top to the bottom, or vice versa. Okay. Now, let's look at if we raise a power to a power. What I mean by that is, say I have x squared, and then I raise that, we'll go to the third power. Well, a power is repeated multiplication. So what this is saying is we have x squared times x squared times x squared. And we learned earlier that if we're multiplying powers, we can add them together. So we just have repeated addition. We're multiplying 2 3 times. So we get x to the 6th power. And we can generalize this since we have repeated addition, which is multiplication. So x to the squared to the 3rd power is the same thing as x to the 2 times 3, which is x to the 6th power. And if we wanted to write this for general terms, if I have x to the n raised to the m power, that's equal to x to the n times m. A second to get that down. All right, and just look at a couple examples of this. So if I had a product of powers, say we have 2 cubed times 2 to the 6th, we'd add 3 and 6 together to get 2 to the 9th. For a quotient, if I had 2 to the 5th power divided by 2 cubed, we'd subtract 5 minus 3, which is 2 squared. Okay. Negative exponents. If I had, we'll use 5 to the negative 1st power, it'd be the same thing as 1 over 5. And for power to a power, say we had 3 cubed to the 5th power, I would multiply my 3 and my 5, so we'd get 3 to the 3 times 5 is equal to 3 to the 15th power. Okay. Should be a little bit of a review. I know you use these in Algebra 1. I think some of them use a little bit in geometry, but not too much. But nice little review because they'll be useful to us later. Another thing we're going to want to review is simplifying our radicals. This one I know you used in geometry, especially when you were working with circles. When we're simplifying radicals, what we're going to do is we're going to try to look for pairs. We want to find pairs because they're perfect squares effectively. So we should know square root of 4 is equal to 2. The reason that is because 2 times 2 is equal to 4, right? So if I can break 4 down into 2 times 2, I have a pair of 2's. Whenever I have that pair, I can bring it out, so we get 2. So what we're going to do is we're going to try to break down whatever's in the radical down into factors. Try to identify any factors that you can bring out. In this case, I recognize that 54 is divisible by 2, so I'm going to factor out a 2. Okay, what's left over is our 54 divided by 2 gives us 27. So we have 2 times 27. All right. And then I know that 27 is 3. The 3 goes into 27, because 27 divided by 3 is 9. And I know that 9 can break down into 3 times 3. So I have 2 times 3, and my 9 will break down into another 3 times 3. Okay, and let's see how many pairs we have. Well, I have a pair of 3s, so we can take that out of our radical. So my 3 comes out of the radical, and then my 2 and my 3, they don't have a pair, so they're going to stay inside. So 2 times 3 is left inside. We could simplify one last time. 3 is equal to the square root of 2 times 3 is 6. It's our general gist for simplifying radicals. This specifically is a square root. We'll look in a moment at what we can do with some of the higher roots. But let's do it with some variables. So let's start with our number. Let's break it down. We have a square root here, so we're looking for pairs. I know that 78, it's an even number, so it's divisible by 2. So I can divide out a 2. 78 divided by 2 will give us 39. Okay, so we have 2 times 39. Feel free to use a calculator too if you have one to help you simplify. I know that 3 goes into 39 because 3 plus 9 is 12. 12 is divisible by 3. Remember some of our divisibility rules back from elementary school. But, and 3 goes into 39. 39 divided by 3 will give me 13. I can erase that instead of just crossing it off. We get 13. So we have 78 is equal to 2 times 3 times 13. And everything else is still staying the same in there. Notice how we don't have any pairs here? Well, if I had a pair, I'd take it out, but in this case, there's no pairs. So the 78 is going to stay under the radical. That's okay. Now we can multiply all these back together to get our 78. Since it can't simplify any further. And let's look at our variables. I'm looking for pairs, so I'm going to break my x squared up into x times x times x. And I have a pair of x's, so I can take that out of our equation. And let's do the same thing with the y's. We'll have y times y times y times y. And I have 2 pairs of y's. Okay, so let's take these out. Square root 78 stays in here. I have 1 pair of x's, so I bring out x. I have 2 pairs of y's, so I'll bring out y and y, which is y times y is y squared. And left on the inside, I still have my 78 and an x. And we're done. Something that it might be, if you can recognize it, if we have an even power on the inside, we're just looking for how many pairs there are, right? Well, if it's even, it can be broken up into pairs. So all of it should come out. So in this case, 4 divided by 2 gives us 2. So we should have 2 pairs if I break it down. But if not, you can always break it down, chunk it into pairs. All right. I want to, yeah, we'll do this one together first. Then we'll have you do an example. So now there's something different about this one. You notice how we have a 3 here? This is where we're getting into Algebra 2, where we have more than just square roots, but in this case we have cubic roots, and the degree can go higher. Generally, we just write nothing there if it's a 2, and we write the number if it's anything higher. It's a very similar idea to our square roots, but this time, instead of looking for pairs where there's 2 of them, right? Because this is like we had a 2 out there, so we look for sets of 2. Since there's a 3 out here, what we're going to be looking for is 3 factors. Okay, same idea. Let's try to break down this 50. I know that 2 goes into 54 because 54 is even, so I'll divide it out. We get 25 plus 2, so we would get 27. So we have 2 times 27. I'll leave everything else the same for now. We can worry about them in a second. I know 3 is going to break down because, or 27 is going to break down because 3 goes into it. So we get 3 times 9. Oh, don't need this 3 here. Oh, give me my eraser, please. Thank you. So 27 divided by 3 is 9. So our 27 breaks down into 2 times 3 times 9, z to the 4th y cubed. Still have that 3 out there. And then 9 is divisible by 3. So 9 divided by 3 is 3. So we have 2 times 3 times 3 times 3, z to the 4th y cubed, and this is all the cubic root. Now, like I was saying earlier, we're looking for a set of 3 factors that are the same. In this case, notice how we have 3 times 3 times 3. That's a set of 3. I can take that outside. The cubic root means what number times itself 3 times is equal to what's on the inside. In this case, 3 times itself 3 times is our 27, so we can take that out. So take out our 3. 2 stays inside. Z to the 4th and y cubed are still in there. This is all a cubic root. Now, let's break up our z to the 4th and y cubed. What we're looking for are sets of 3. So that 3 on the outside, 2 on the inside, and let me break my z down into z times z times z times z. Okay, and I'll break my y down into y times y times y. Let's see if we have any of those sets of 3. For my z's, I have 4 of them, so I have 3 in there. And if we can recognize the 3 from here, we don't have to write them all out. Similar for our y's, we have 3 y's, so we have a set of 3, so that's going to be able to come out. So in front we have our 3z, our cubic root of 2, oh, forgot our y, let's move that over. Cubic root, we have our y on the outside because we also had a set of y's. We have 2 times, left on the inside we still have a z. And that would be the simplified radical. Very similar to square roots like you've done before in previous classes. It's just now when the power increases, instead of looking for perfect squares or pairs of 2, we're now going to look for perfect cubes, or it's easier to identify, it's just sets of 3 factors. I want you to take the next couple minutes to give this one a go. Try to simplify this square root. Okay, if we got a chance, and this should simplify down to 2x cubed z squared times the square root of 3x. Okay. Now, let's get into what we can use to adjust our radicals into exponents. Now, these are our radicals here. The ones that have this radical shape to it, it's our square root, our cubic root, those are all radicals. These are, you notice, what the radical is really representing is it's like a fraction inside of the power. So this index that we're working with, that's the square root, for instance, has an index of 2. This would be an index of 2. If we had a 3 there, we'd have an index of 3. Whatever it is, that, let's see if this is going to freeze. Okay, there it goes. That blue value here, whatever that number is, goes into the bottom, and vice versa. They can go back and forth. So we're going to look at kind of converting back and forth between radical form and having rational exponents. So we call these rational exponents. All right. And our m on the inside, that's our green, is going to go to the top. All right. So, it's a quick example. Say I had the square root of 2 to the 3rd power. This would be the same thing as my base is my 2. My root is our square here. So it's the bottom of our fraction. And our power is the 3, which goes to the top of the exponent. These just can convert back and forth. They're equivalent. All right. So let's look at another example. So if I had 2 times 8x to the 3 over 11, well, 2 is not connected with this exponent, but if I wanted to turn this into a radical, my 8x stays in here. That is our base. Whatever is being raised to the power, that's your base. So this, our 8x, goes on the inside. The bottom of our fraction, our 11 here, that becomes the index of the radical. And the top value, or 3, becomes our power inside of the radical. Okay? Let us look at another one of these. So say I had 10x raised to the 2/3 power. If I wanted to turn this into a radical, we have a radical. The base is whatever's on the inside, whatever is being raised to a power. So it's going to be 10x. The index is going to be the bottom of the fraction, goes on the outside. And the power on the inside is the top of the fraction. Okay? Now, what I want you to try is, actually, let me Let me write up another one. I want you guys to try one. Okay. So what I want you to do is take a couple seconds to turn this expression with a rational exponent into a radical. Let's give it a go. Alright, and what you should have gotten is our x to the third power with an index of 5. Base, whatever in here, top of the fraction goes on the power on the inside, bottom of the fraction is the index. Alright. Now, let's try to go the other direction with it. So, if I have x to the 8th on the inside, my base is going to be the x. Okay. My base is our x. The top of my fraction is the power on the inside. And the index on the outside is the bottom of the fraction. Then we're done. We wrote our radical expression with a rational exponent. Okay? Now, I want you guys to give this one a go. Take a couple seconds, try it out, and we'll go over it in just a moment. Okay? And what you should have gotten is z to the 3/2. If we don't have an index here, it's a 2. It's our square root. It's the general one we use for it. And that goes on the bottom. Power on the inside goes on the top. Okay, let me... Just one sec. I want to add something in before we do this. Okay. This is... Alright. So, something I want to do before we go on to that one. Come back in. So, we only had a single base on the last couple examples we did. I want to look and see what happens when we have multiple bases. So say we have 15 times x cubed. Okay. And we'll put a y squared in there too. Or, yeah. Okay. So, if I wanted to turn this into a expression with a rational exponent, what we're going to do is we're going to treat each base individually. Okay? So let's start with our base of 15. So we have 15. It's to the power of 1. So the power on the top is 1. And our base, or our index for all of it is 2. Okay, let's look at our next term. Our x has a power of 3, so that's our top of our numerator. And our index on the bottom is going to be 2. From here. Okay, and let's look at our y. So we have y. We have squared on the top. And we have our 2 on the bottom. If you notice, 2 divided by 2 is 1. So the square root of y squared is the same thing, still just y, even if we change it into our rational exponents. So I'll simplify this. We have 15 to the 1/2 times x to the 3/2. And then 2 divided by 2 is just 1, so we have y. Okay. Now, I want to make this a little bit tougher. It's like a little bit of a tougher example. So, in our example here, we have a radical that is being raised to a power. So notice this is on the outside. What we're going to do is I want to deal with everything on the inside first. Then we'll look at this on the outside. Alright, So we still have our radical here times 5 to the x. We have a 4 for our index out here. I want you to notice, say we have two bases. We're going to break it up separately like we just did. So looking at our first term, our 10 is raised to a single power and has an index of 4. So we'll have 10 to the 1 over 4 times our x is our base. It's being raised to the 5th power and has an index of 4. Okay, and then all of this is being raised to the 3 over 10 power. Now, if we remember from the beginning, told you our laws of exponents are going to come in handy. If we have a power being raised to a power, like we have here, if we go back, if we have a power being raised to a power, what we do is we multiply the exponents. So let's go back to our problem. So I have a power to a power. So what I'm going to do is I'm going to multiply this power to each of these. So we have our 10 to the 1 over 4 times, is it going to go through? 3 over 10 times our x to the 5 over 4 times 3 over 10. So we have our fractions that are multiplying here. And if we remember our multiplying fractions back from 3rd or 4th grade, multiply across the top. 1 times 3 gives us 3. 4 times 10 gives us 40. And for our x here, multiply across the top. 5 times 3 is 15. 4 times 10 is 40. Okay. Let's see if we can look at another one. It's a little interesting. Okay. So, if I want to rewrite our rational exponents, we're going to treat each of our different terms individually. Okay? Now, let's look at each of our terms. Let's start with our 3x squared. So my base, I'm going to start with the 3, not the x squared. You can do, see if my pen will come back. Alright, let's start with our 3. 3 only has a power of 1. So we have 3 raised to the 1 divided by the index of 5. Let's go to our next term. We have our x squared. Our base is x. It's being raised to the 2nd power. We have an index of 5. Okay, let's look at our y's. We have y. It's being raised to the 4th power divided by the index of 5. And on the bottom of our fraction, we have our, I'll use red again, it's a constant. We have our 8. I should just underline that. We have our 8. 8 is being raised to 1st power and has an index of 5. Our z is being raised to the 15th power and has an index of 5. So you just treat each term individually, even though it's on the top or bottom of our fraction, doesn't matter. Alright, And I know it's getting a little bit of a long one. We have one more topic to cover, and that's going to be our domain. Okay? Now, in the past, when you have taken square root of x squared, we had multiple answers that came out. We had a positive and a negative version. So say we had the square root of x squared is equal to 5. Our two solutions for x could be either equal to plus or minus 5. It could be either or. So what's happening here is if I had a negative value in for x, say we'll look at the negative 5 here. Well, negative 5 times negative 5 take the square root of that. Well, negative 5 times negative 5 is 25, and my square root of 25 is equal to 5. Should be a little bit of a review, but if I plug in a negative number, if I square it then take the square root, it's going to come out as a positive. Similar idea is going to happen with higher degree or roots of a higher power as well. So let's say that we're looking to take the fourth root of x to the fourth power. And we'll make this equal to, let's say, 3. Similar to our square root, whenever this power is even, right here, all my answers that come out, there's going to be a positive and a negative version of it. Reason being, let's plug in negative 3 as a solution here. Negative 3 times negative 3 times negative 3 times negative 3. When I multiply all of these together, I have a negative times a negative, which makes a positive, and a negative times a negative, which is a positive. All of my negative signs are going to go away, and when I take the fourth root of this, it all comes back to just that positive 3. But for our excuse me, for our general rule, if the index is an even number, we have the positive and negative solution. Pretty much when you take it out, it's going to have to be one or the other. Similar to our absolute value functions, which you guys have worked with recently. We'll cover more on our domains in class, but when it's an even number, we're going to have a positive and a negative for our answer. Okay? And a lot of the times, the way we'll write the answer is because the absolute value is so similar, we'll just do absolute value of x. So for our answer for here, for plus or minus 3, we just have the absolute value. All right. Try to wrap it up since I know this was a rather long video, several crunched together. Hope you guys have well, I guess I should put it in. If it's an odd number, this even part's very important. If it's an odd number, this doesn't apply. Well, if your index is odd, if you'll give me a marker, it doesn't matter. But if it's even, we're going to have that positive and negative solution. All right. Hope you guys have a great rest of your evening. See you in class.